Morning. Today's topic is internal faults. Today we'll derive an expression for the minimum internal fault current that can be determined by the differential scheme. In the last video lecture, we have discussed the external faults and how a saturated CT will give a false alarm for the external faults. And we have opined that if we keep a high value of resistance in series with the overcurrent relay in the differential scheme, then it will help us in stopping this false alarms. And that particular resistance is called as stabilizing resistance. And we have also derived an expression for the stabilizing resistance, isn't it? Now, its value is equal to V set by I pickup value, and this V set is to be adjusted such that your maximum fault current is being met. So now, in today's class, we will determine an expression for minimum internal fault current which can be detected by this high impedance bus bar differential scheme. So using of this high impedance is inevitable for us in order to stop this false alarms. So there is a problem with this placing of high impedance in the circuit. We may get, or because of the presence of this high impedance, there may be a chance that the current which is flowing in the circuit may be less than the actual value, which may not give an alarm for internal faults also. So in today's class, we will see what is a minimum internal fault current which can be detected by this high impedance differential scheme. So I'll start with the representation of internal faults. We'll take a single phase bus bar system, and then I'll show you what actually an internal fault is, and then we will try to determine an expression for internal primary currents, internal fault current. So let us define this particular one. The minimum internal fault current is being defined by this particular term, I fault due to internal fault, and I'm more concerned about primary currents, not on the secondary currents, right? So this is to be determined today. So first of all, let us assume that the CTs are not saturated and the high impedance, see, whatever the coils which are coming from here, there is a high impedance, and also this is a stabilizing resistance which is already present. Sorry, RS, or I'll write it as R stabilizing, not to get confused with the secondary resistance. So I am representing it as R stabilizing, and this is my overcurrent relay here, and this voltage is my V set, and this overcurrent relay is having a pickup value of I per unit. So the high impedance scheme has a pickup value of IPU, a stabilizing resistance of R step, and therefore needs a minimum voltage of V set to be developed across this particular combination of series stabilizing resistance and the overcurrent relay. Now, let us try to determine the minimum fault current. If you see the scheme now, right? See, this is your R stabilizing resistance, this is your overcurrent relay. Normally there will be a small resistance also. If you want to consider, you can consider, or otherwise you can neglect that one. It is of very minute value when compared to your R stabilizing resistance. So this entire voltage is your V set voltage, and this is your current which is flowing through this one, right? So normally if I neglect this particular resistance, and this is the fault current, minimum fault current which is to be detected, this is secondary. Okay, secondary current is flowing in the circuits. Primary current will be flowing in the main circuit. Secondary current will be flowing in the relay circuit, right? So my V set is equal to IF minimum, this is secondary currents, into R stabilizing resistance. Or in other words, if I want this one, I can write it as V set by R star. But literally speaking, this is actually my pickup value, right? So which means that your minimum fault current which is to be detected must be equal to your pickup value. If it is greater than this pickup value only, then only you will be detecting any internal fault in the circuit. So now see, this is a representation of an internal fault. See, this is a single phase feeder, take it as a single phase feeder. Two incoming feeders are there, one is actually an outgoing feeder. So this is the actual circuit. Two incoming feeders, this is a single phase bus bar. A, B are incoming and C is an outgoing feeder. But since there is a fault happening here, the currents will be flowing in this way, and this feeder also now acts as an incoming one, isn't it? So now that's why I have represented here. See, IC is also now acting as an incoming one, and this is your internal fault which has happened here. Now there are three CTs which are present here. This is CTA, and this is CTB, and this is CTC. Now all are carrying secondary currents, and this current is being passed through this one. Right. So this is my overcurrent relay, this is my stabilizing resistance, isn't it? So this is my one current and this is my another current. Right. Now if I draw the equivalent circuit of this one, see, this is the equivalent circuit of my CTA, which I have shown you in the last lecture also. This is my secondary one and this is my third feeder. These are the equivalent circuits. See, these are not saturated ones. These are all assuming that these are all unsaturated CTs. Okay, so assuming that these are all unsaturated CTs, now see here, everything is being represented by their currents. Now all these currents now flow into this circuit. Now see, what is the entire current? This current plus this current plus this current, everything is being flown, and this is now supposed to flow through this one, isn't it? So the minimum secondary current which is flowing in the circuit is equal to, which is also equal to your pickup value. This is current from CTA, this is current from CTB, this is current from CTC. See, these are IA, IB and IC, or the primary currents which are flowing in that CTs, whereas these are the leakage currents, and N is the turns ratio or transformation ratio, whichever you pick up. So if I rearrange the terms, see, this is the rearranged term. I'm getting all this magnetization currents to this side, and these are the main currents, primary side currents. If you carefully see, if I take these things as common, this is IA plus IB plus IC. This is what the fault current is. All the three currents from the feeders going into your fault resistance, isn't it? So this is your IF minimum primary sides by N minus, this is magnetizing currents, right? Assuming all the three are basically identical, and if I represent I naught as a magnetizing current, so this can be written as 3 I naught. So this is equal to your IPU. You know, IPU is nothing but here V setting by, right, which is nothing but here V setting by R stabilizing, isn't it? So now if I write these equations here, I per unit is equal to minus 3 I naught, right? So if there are n number of feeders which are flowing into the system, so if n represents the number of feeders, then here instead of 3 I will write it as, this will become n here, isn't it? So if I rearrange this equation, now what I will be getting, this minus 3 I naught, it will be going here, and this one also will be going here. So this is my equation, n into IPU plus 3 I naught. If I generalize this one, this is my expression, isn't it? So this is the pickup value of the current. So whatever the minimum primary fault current for internal faults is equal to n into IPU plus n into I naught, where n is the number of feeders, IPU is the pickup value of the relay, I naught is the magnetizing current of any unsaturated C2, assuming that all are identical. Assuming all are identical. All CTs are identical. And n represents the turns ratio. Okay. So this is the formula for minimum internal fault current that can be detected by the high impedance busbar differential scheme. Okay. So this high impedance busbar scheme, it is inevitable for us to protect our circuits and also for protection against false alarms. And despite using this high impedance busbar scheme, you are supposed to determine the minimum internal fault current. So I hope that now you are able to explain me the procedure of determining the minimum internal fault current. And there are problems in this one. We will discuss them in the class. So first of all, lectural practice questions. This is your derivation which you are supposed to do in detail, and this is the problem which you are supposed to solve in the class. See, the overcurrent relay is being, this is your pickup value. This is in continuation with the problem which we have done in the last class. This is the voltage setting. Find the minimum fault current that can be detected by the differential scheme. So what they are asking, internal primary. So try to solve this problem, and we will try to solve it again in the class, regular class. Okay, thank you.